Hi, this is a three-part video that aims to give a deeper insight into quantum mechanics than you might be used to, and will try to barely touch upon the mathematical side of the theory, but my aim is to get across the ideas of how quantum mechanics works. This is because most videos on quantum mechanics that I've seen just describe experiments that show the effects, but leave you utterly baffled as to how they actually happen. Or the description is embedded in a long lecture course aimed at people who already know enough physics to be able to cope. The aim here is to be a happy in-between. Now, part one is the setup, explaining some of the basic tools needed to do quantum mechanics. The second part aims to explain the mechanisms behind quantum mechanics. And the third and final part aims to look at these experiments and show how they are predicted from the underlying theory. If you have any questions about what I say or you want me to go over something in a bit more detail, please feel free to ask. I'll either make another video or talk to you in private about it. Okay, so quantum mechanics. Um, so you know where we're coming from. Let's recap a tiny bit of classical physics. Now, in classical mechanics, particles are described by both the position and the momentum, and both of these properties can be known exactly. And you can know the trajectory for the particle, and you can know it for all of time. And so, given some initial conditions, using Newton's equations of motion, you can describe how the particle accelerates based on what forces it experiences, and from that you can know its position and its momentum. So the system is described perfectly by how the momentum and position change in time. Now let's imagine you had a full description of the system, you knew where all the parts were and how fast they were all moving. From this you can work out all dynamical observables that can be found from the system, such as angular momentum, energy density, current flow. You can find all these out using just the position and the momentum. Importantly, whenever the system has the same momentum and the same position, it will have all the same values for all the observables and will follow the exact same trajectory. And it will do this every time it has the same position and every time it has the same momentum. Now this seems quite obvious, which is why I'm stressing it. It'll be one of the first things to change when we move to quantum mechanics. You can think of it as expecting your car to act the same every time you turn the wheel, so provided the car hasn't changed. Now, with this incredibly brief overview of classical mechanics, it's time to discuss a bit of quantum mechanics. The problem is that it's hard to do away with the mathematical nature of quantum mechanics, but I'll try my best to cut away as much of it as I can. This is so as to not hide the wonderful world that it uncovers. But as a result, there will be times when I abuse terminology or cover up technical details or just completely ignore things that are actually there. However, if you can spot these things, you kind of already know more than what I'm going to explain. Now, I said in a classical system, it's fully described by knowing both its position and momentum at all times. In quantum mechanics instead, the system is completely described by a wave function, and all physical information is held in this one function. And in a way, it's the most fundamental thing in quantum mechanics, and for ease, we'll always call this function phi. Now, wave function's just a name given to it for now. Just go with it. But it's called a function because for every point in space, we can get a tiny piece of the wave function. And so when we know the wave function for all of space, it means we know all of the system. This might seem a tiny bit abstract at this point, so I'm going to try and interlace this discussion with a lot of everyday examples. You can think of a room, and now for every single point in that room, you can put a thermometer and you can find a temperature. You have a function that for all of the room, it will tell you how hot it is at any point. Similarly, a wave function will tell you for all of the room something about the system it's describing. For an example of what type of thing it is a wave function actually does tell you, imagine that you did have a particle described by some wave function. Now, you don't have to visualize the entire of the function, that's pointless. I mean, you can't imagine something that's infinitely big. Now, just imagine it for some small volume. If you put a box around that volume, and if you add up all the parts of the wave function in that box, it will tell you how probable it is that the particle is in that box. Now, if you have a box that covers all of space, then the probability of the particle being in that box has to be 1 because there is still a particle. So you can also imagine that there's points where if you put a box, there's zero probability of getting a particle. Now, normally you can only know some wave function for a small part of space, like inside the volume of your experiment. And this is your general everyday problem with physics in that you normally consider everything, but in reality you only have a small part of it. And so you normally have to get some way of ignoring it all. This can be done by considering the fact that quantum mechanics describes things that are really, really small. So when your experiment's just a couple meters big, you're still far bigger than the things you're talking about. And so you can approximate it as the entire of space. Now, like I said, we have a wave function, and it describes everything about the system. But the problem is, how do we get that information from the wave function? Like, what particular values for energy does the system have? Well, for every single observable, so energy, angular momentum, etc., we have something that's called an operator, and it operates on the wave function, cutting it up into tiny pieces. Now, the momentum and the position are some of the most important observables in classical mechanics. Like I said, with these two properties, you can describe the entire of the system. And so these two also need to have some representation as operators that act on the wave function. Now, if the system is described by the wave function and it has a position, an exact position, say x, then we expect to be able to get that exact position when we act on it with an operator and cut it up to find out whereabouts it is. Similarly for momentum, if it has an exact momentum, we expect to be able to operate on it and get the exact momentum. But in physics, you're normally interested about the energy of the system, and so energy too needs to have an operator. The energy operator holds quite a bit of importance in quantum mechanics. But the question is, how do we get these operators? Like, it's fair enough to say they exist, but surely you need some way of finding them. For this, we need to go back to classical mechanics. Recall I said everything in classical mechanics is described by position and momentum. Normally they have a formula that given position and momentum will tell you the energy or the angular momentum or the current or whatever it is you really want. So we'd expect something similar to carry into quantum mechanics. I mean, these equations don't come from nowhere. Basically, we're using classical mechanics as a guide to get towards a more accurate theory for describing the world. So, for energy, the total energy of the system can be given by the kinetic energy from the moving parts plus the potential energy from forces pulling and pushing on the system, like gravity pulling it down to the Earth. The equation for kinetic energy is the kinetic energy T is equal to the momentum squared over 2 times the mass. Meanwhile, for the potential energy, which is always called V, it normally just depends on the position, x. So the total energy is energy equals kinetic plus potential, which is equal to the momentum squared divided by 2 times the mass, plus the potential energy, which depends on position. Now, I've not really said anything that's quantum in this statement. It's just a normal function that you would get for energy, for momentum and position. But recall I said that momentum and position have to be operators in quantum mechanics. We can promote the momentum and the position into operators inside of our equation for energy. This in turn will give us an operator for energy. It will go into your wave function, cut it up and find out the energy. This is brilliant. Briefly ignoring any technical details, but just in case you're interested, the position x becomes the operator f of x equals x, and the momentum operator is I h bar d by dx, where h bar is just some constant normal. It's normal to pick up a constant here and there. And these operators are only equal to this when we are in the position representation. Putting this all together, we find the operator that acts on a wave function phi to be minus h bar squared over 2m d2 by dx squared plus the potential energy, which is a function of the operator x. This acts on the wave function phi to give you the energy times by phi. Now this is an equation for the energy E, and it is called the Schrödinger equation. And we can solve this and get out both the wave function for particular energy as well as the equation for that energy. I know I said I'll try and cut out the maths, but let's just quickly look at this. It will enlighten why we call it a wave function. Let's consider the case where there's no potential energy, there's no forces acting on our particle. Then we can work out the equation for phi. This is done on the screen in front of you. I'm not really going to talk it over. You can pause it if you want to look. Importantly though, we have no restriction on what the energy E can be. This is kind of good because you'd expect a particle with nothing acting on it to be however energetic as it wants. I mean, there's nothing happening to it. But importantly, the solution is a wave. Cos theta is a wave, sine theta is a wave. The I is a complex number, it means that it's a weird type of wave, but it's a wave nonetheless. Hence, wave function. Now, phi here is an example of what's known as an eigenfunction. And these are very, very special to quantum mechanics. In fact, they're very, very central to the entire ideas behind it. In fact, they are so very central that they are the topic of the next video, which actually gets to the meat of the matter.